Hey, space enthusiasts. Have you heard people talking about how we may be able to produce things like better drugs and better semiconductors in space? One does hear that type of thing more frequently these days, especially with companies like VADA in the US testing capsules that are intended to enable this type of activity. For many people, that still sounds a little futuristic, but indeed, there's already a lot going on in the domain of in-space R&D and manufacturing. In my view, it has the potential to become one of the next big space applications, following the traditional and already established ones like satellite communications, remote sensing, and position navigation and timing. Therefore, I have decided to record a series of episodes that will explore in-space R&D and manufacturing. This is the first one. I'll be right back after our usual short intro.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
So as I said, this is the first episode in a series of episodes on in-space R&D and manufacturing that I'm planning. This is a solo episode by yours truly. Over the next months, we will have further episodes where I'll be joined by relevant guests. One important caveat, we will mostly focus on in-space manufacturing of products for use on Earth. There's also in-space manufacturing of products for use right there in space. We'll focus on the former, as that intuitively has to be the bigger commercial market for the foreseeable future. That doesn't mean I'm not interested in the latter. Much to the contrary, and perhaps we'll end up having 1 or 2 episodes on that market segment. In this first episode, though, we will try to answer 3 questions over the next 25 minutes or so. Why would one research and maybe even manufacture in space? How can it be done in practice? And what is the current status of in-space R&D and manufacturing? And ultimately, how can we build a thriving in-space manufacturing economy from where we are today? We will close on me explaining why I think now is the right time to look at in-space R&D and manufacturing, and an exciting, relevant, recent announcement. Okay, so first topic. Why research and manufacture in space? Well, indeed, why? Going to space is still complicated and expensive. It sounds just about as crazy as wanting to produce things in Antarctica or in Mount Everest. Well, first, let me ask you a question. Why do the world's best wines come from a few relatively small regions? There are probably a few reasons, but they include what's called the terroir in viniculture, the soil, and also the climate. Some places just have particularly good conditions for growing wine, and you can't just replicate them in other places easily. Space also has such special conditions, and a few of them. Special, that is, relative to what we normally find on Earth. One very simple but important example of that is the fact that space allows a better vantage point than being on Earth, with respect to the Earth. We've taken advantage of that special vantage point for satellite communications, for remote sensing, and for satellite navigation. That special vantage point is also nice for astronauts, including private astronauts, looking out of the window of a spacecraft. Other special conditions, though, include a variety of regimes with regard to environmental variables, such as, for example, temperature, pressure, and perhaps most notably, gravity. There are also some other environmental conditions, including that space is often a high radiation place. So why would you care about those special conditions in space? I can think of 2 main reasons. One, you want to test something that is eventually supposed to operate in those very conditions, say components of satellites or a spacesuit. Or 2, the conditions allow you to do something you cannot do on Earth, or at least not as well or easily. Let's zero in on one special condition, gravity. Why? In part, as we don't know how to replicate different gravity regimes on Earth, at least for sustained periods of time or without undesired side effects. Even if we did, by the way, it would still have to be at a commercially viable cost. For gravity, you probably know that we use the G unit. On Earth, we experience 1G, at least under normal circumstances. That is, for example, if you're not jumping out of a plane and are in freefall. On the Moon, it's 0.166G. which is why it was so relatively easy for the Apollo astronauts to hop around on the lunar surface despite their heavy spacesuits, including the backpacks. On Mars, it's 0.38 G. In the atmosphere of Jupiter on top of the clouds, around 2.5 G. And if you are in permanent freefall in orbit, for example on the International Space Station, you experience what's called microgravity, or colloquially and incorrectly, 0G, it's not exactly zero, or weightlessness. Importantly, microgravity turns out to have all sorts of interesting physical follow-on effects. For example, there is no sedimentation and buoyancy. That is, for example, if you mix a higher and lower density substance in a fluid, on Earth, the lower density substance floats to the top, and the higher density one sinks to the bottom. In microgravity, any kind of growth, say of a crystal, happens uniformly in 3 dimensions. There's also no convection in microgravity. One impressive and well-known example of that is that a flame in microgravity is spherical rather than the shape we know on Earth. There are all sorts of effects on the human body. For example, there is less mechanical stress on your bones, so they start dissolving, which in turn has effects such as that there's a higher risk from kidney stones due to the increased calcium in your blood. Your heart also has to work less to pump blood up in microgravity, and it therefore deconditions. In general, fluids in the human body redistribute from the lower body to the upper body, causing effects like thinner legs, facial swelling, and even vision impairment. The immune system seems to weaken, and the list goes on. We could have an entire long episode just on this subtopic. In any event, these effects of microgravity can be used to do interesting things. For example, we can bind things that don't bind on Earth. We can mix things that don't mix on Earth. And we can construct or grow things in 3 dimensions that would collapse on Earth. More specifically, for example, under microgravity you can produce higher purity optical fiber, so-called Z-blan. Under 1G conditions, the same optical fiber has more impurities, leading to a higher signal loss. You can produce better semiconductors. You can produce better alloys, which we would not be able to produce under 1G conditions on Earth. You can produce better emulsions. An emulsion is a mixture of immiscible liquids. Think oil and water. This is relevant, for example, for cosmetics and pharma use cases. We can perhaps produce better materials for things like athletic shoes or automotive brakes. Both of these are actual use cases that have been explored by relevant commercial customers. We can possibly produce more resistant agricultural seeds. We can produce better protein crystals, which enables more efficient designs of new drugs that target such proteins. Or in the case of protein-based drugs, that is where the drug itself is a protein, you can design a better seed crystal in microgravity. You can grow organ tissue in 3 dimensions into so-called organoids that can be used for biological testing, including drug testing, and also for regenerative medicine. On Earth, such 3-dimensional cell models of any meaningful size need to be supported by so-called matrix or scaffold, and that introduces undesired foreign materials into the biological tissue. We may ultimately even try to 3D bioprint entire replacement organs in space. In microgravity, we can also study disease models where the disease condition is accelerated or otherwise altered in this special environment. For example, as we already discussed in microgravity, bones start to dissolve, so we have already made use of that to develop osteoporosis drugs. We can produce replacement retinas by very cleanly layering a certain protein hundreds of times, whereas on Earth the whole thing would just collapse after a few layers. The last example, by the way, is done by a startup called Lambda Vision, and that's a company my venture capital fund invested in. Many of the other use cases I just mentioned are also already pursued by startup companies. In general, when we talk about the research and manufacturing use cases in microgravity, these use cases fall into roughly 2 big buckets: life sciences and advanced materials. As discussed, then there's also testing or even production of things for use in space, and we will leave the details of those for a separate episode or episodes. Second question: how can you research and manufacture in microgravity in practice? Well, you need some sort of platform that provides you with microgravity. One really important caveat before we discuss microgravity platforms that are actually based in orbit: you can achieve microgravity on Earth, that is, without going to space. So anyone proposing a business that requires microgravity does have to answer the totally reasonable question of whether going into space, with its additional cost and logistical challenges, is really required. Here's the caveat to the caveat. We cannot achieve microgravity on Earth for a sustained period of time or in a, for the lack of better word, clean way and without side effects. Let's quickly review what these Earth-based microgravity alternatives are. A drop tower is exactly what you imagine from its name, a big tower where you drop something from the top, which then experiences a free fall and microgravity during the drop, lasting a few seconds. There's, for example, a 150-meter one at the Center for Applied Space Technology and Microgravity in Bremen, Germany, and it produces about 5 seconds of free fall. You yourself can experience the same effect in one of those amusement park drop rides, or bungee jumping, or skydiving, or if you were unlucky enough to be in an elevator and the elevator cable tore and the elevator car dropped. For experiments requiring more than 5 seconds of microgravity and or more physical space, the second option are so-called parabolic flights. As the name suggests, an airplane repeatedly flies parabolas. At the apex of the parabola, between the climb and descent, objects inside the plane experience microgravity for typically around 20 to 30 seconds. NASA conducts such flights in order to train astronauts for the microgravity conditions they will experience during actual spaceflight. Parabolic flights, also colloquially called zero-G flights, are offered by various private companies for both scientific and recreational purposes, for example, the American Zero Gravity Corporation or the French Air Zero G. A different way of achieving microgravity on the ground, or more correctly, simulating microgravity, is by using contraptions called clinostats and random positioning machines, or RPMs. In such machines, a relevant sample, say a sample of biological material, is continuously rotated so that the gravity vector gets neutralized. Clinostats use one rotational axis and RPMs too, but we won't go into further detail here. In any event, while these machines can operate for long periods of time, they have disadvantages, namely, 1, the neutralization of gravity may not be complete, and 2, there may be undesired side effects like shearing. And it has been shown experimentally that the effect of microgravity simulated in this way is not the same as the effect of true microgravity on biological materials anyway. So let's go into space now for true microgravity. After all, this is the Space Business Podcast, not the Parabolic Flight Podcast or Clinostat Podcast. Before we go into freefall in Earth orbit, we have to mention for completeness that you can achieve up to a few minutes of microgravity on suborbital flights. This can be achieved on so-called sounding rockets, such as the European Texas or NASA's Orion, or now also on the well-known human suborbital spacecraft operated by Blue Origin and Virgin Galactic. Okay, let's finally go to orbit. There are a number of platforms that allow achieving continuous microgravity being in freefall in an Earth orbit. We can divide them into two main categories: space stations and free flyers. These terms are fairly self-explanatory. A space station is a structure that remains in space, while a free flyer is a spacecraft that flies up to space and then also back to Earth. During its time in space, such a free flyer may or may not dock with a space station. Let's start with the platforms that are currently in operation. The best known space station has to be the International Space Station, or ISS. Since 2000, about 3,300 experiments have been carried out aboard the ISS by more than 4,200 researchers from 108 countries. Besides materials, on the life sciences side, such experiments have been conducted on models ranging in size from bacteria, over cells, ants, worms, zebrafish, rodents, all the way to humans. No elephants or whales yet, for perhaps obvious reasons. Surprisingly, many people, at least outside the space community, still don't realize that humanity has another space station in orbit right now, the Chinese Tiangong, or Heavenly Palace. Like the ISS, Tiangong orbits at around 400 kilometers altitude above the Earth. It has a core module and 2 lab modules. as of mid-2023, according to China Daily, Tiangong has already hosted 110 science and technology projects, and it only became operational at the end of 2022. Moving from currently operating stations to currently operating free flyers. There's, of course, the SpaceX Dragon capsule. And Dragon, of course, mostly goes to and from the ISS, but not only. And yes, you can fly experiments on it. And that happens, for example, on the company's high-profile private explorer missions, such as Polaris or the very recent Fram-2 polar orbit flight. There are other vehicles that service the ISS, namely Northrop Grumman's Cygnus and Russia's Soyuz and Progress. And among free flyers, there is even a spaceplane operated by the US Space Force, the X-37B. And now you have the private American company VADA, who has so far flown and brought back its small capsule 2 times already. Now let's look into the future and what's upcoming. Among future planned space stations, we have a few, in part driven by the known need to replace the ISS, which is currently expected to be phased out by 2030. NASA's CLD, that is Commercial LEO Destinations program, is meant to find one or more replacements for the ISS. They're in alphabetical order: the Axiom station by the American company Axiom, which is meant to start as an attachment module to the ISS before becoming an independently flying station. There's Orbital Reef, which is Blue Origin's proposed space station. Starlab, a consortium formed of a few companies, and VAST, another American company. I also expect we'll see more sovereign space stations in the future, such as India's proposed BAS, planned to become operational by 2035. For future free flyers, we have, for example, Atmos, a German company with a small capsule, which will fly very soon on its first test flight. Catalyx from India, formerly known as Space Rickshaw. The French-German exploration company with its Nix capsule, which is also supposed to fly in 2025. It actually already had a first subscale prototype on an Ariane launch last year, but it failed to achieve its objectives due to an anomaly with Ariane's last stage. There's also Inversion Space from the US, Orbital Paradigm from Italy, Outpost, another American company that has mentioned semiconductors and ZBLAN as target areas, Sierra Space with its Dream Chaser spaceplane, Space Cargo Unlimited from Luxembourg that wants to operate a version of the European Space Rider spaceplane for in-space experimentation and manufacturing, Space Forge from the UK with its Forge Star spacecraft and wanting to focus on semiconductor manufacturing, and of course Starship. As a reminder, SpaceX's next generation rocket is a 2-stage fully reusable vehicle, meaning even the second stage will usually come back from space, making it a viable vehicle for in-space experimentation and manufacturing. I know I'm forgetting or leaving out people here. Partly that's companies that I still think are in stealth mode or otherwise very early on, but I may actually forget some that I should mention, so please do ping me if you're working on this type of platform. As you are probably aware, I'm deeply involved in the topic of in-space R&D and manufacturing beyond doing podcast episodes about it. With so many options, how do you actually choose, including the interesting question of whether to choose a space station or a free flyer? Well, it depends mostly on your requirements. For example, what do you need in terms of space and volume, power, environmental variables such as temperature, pressure, and so on? Is there any specific fixed equipment you need? For example, an induction oven or a DNA sequencer. Importantly, do you need human intervention? On that question, by the way, from a cost point of view, it's better if you don't, because astronauts need to be flown to and from orbit and kept alive, and that is still very expensive, which is why NASA charges out astronaut hours at about $130,000 per hour. Another question is whether you need to come back to Earth. That may not be the case for some experiments. Sometimes data can be gathered right there on orbit and simply transmitted back to Earth. That is, you send back electrons or photons, depending on your mode of communication, rather than atoms. For example, you may conduct personalized medicine or drug testing on orbit and just send the results back, rather than any actual materials. At other times, though, you need to bring materials back to Earth. For example, when further required analysis is only possible on Earth, or of course, for any use case that is actually producing commercial products in space for use on Earth. If you do need to come back to Earth, there may be requirements you have regarding the re-entry profile of the spacecraft that will be used to come back. Okay, how can you access these platforms? Well, it depends on the platform. For the commercial ones, you can just contact the respective companies. For the ISS, a good way is to go through the participating space agencies, which also often have grant programs to access the ISS. For example, NASA via the ISS National Lab in the US, or ESA via its BSGN program. For some platforms, I can't really help you much, like the Chinese Tiangong station or the Russian vehicles. Anyway, instead of going directly to some of these platforms, you can also go via what is sometimes called an integration partner. These are organizations who can give you access to a platform like the ISS, who know how to do the required paperwork, have capacity on it, and usually have hardware that is already approved to fly and to be operated on a certain platform. We'll get back to hardware in a few minutes. First, though, here are some examples of such so-called integration partners. In the US, Bioserve, Redwire, Rhodium Scientific, Space Tango, and others. In Europe, for example, Kaiser Italia, Space Applications, Yuri. Then there are also Space Pharma in Israel and Space BD in Japan. Now, as I started mentioning above, besides just helping you access microgravity platforms, virtually all of these companies that I just mentioned also offer relevant hardware to conduct in-space experimentation. Not so much to conduct manufacturing at scale yet, to be honest. But if you need, for example, hardware to grow and keep alive biological tissues or to crystallize proteins, among many other things, there are several hardware options out there. And if you can't find the right hardware for your use case, well, just build it yourself. It may become an integral part of your company's intellectual property. On to our third topic. What is the current status of in-space R&D and manufacturing? And how can we build a thriving in-space R&D and manufacturing economy from where we are today? Well, let's switch this around and ask ourselves, what are the pieces that we need to build a thriving in-space R&D and manufacturing economy, and see what we already have and what we still need? The following is just my simple framework, and it may still be incomplete or should be otherwise refined. So personally, I think we need, first ingredient, technologically viable use cases. And I think we have those, thanks to the many experiments successfully conducted in microgravity already. Second ingredient, we need a market with customers who have demand for products based on these technologies. Well, frankly, who wouldn't want better drugs or semiconductors from microgravity? Now, it's not that easy either. Just a couple of points. One, economics, basic economics tells us that demand depends on price. So we need these products at a viable price. We'll get back to that in the next point. Second, potential customers need to be educated. I can tell you this is still a huge problem. Outside the space sector, the potential users of in-space products hold historical stereotypes about space being incredibly expensive and difficult. This will take outreach and education to overcome, and that will take some time. It's the reason why I'm doing a podcast episode like this one. Third ingredient, and related to the previous market one, we need economically viable business models. And this means economically viable for all participants in the value chain. So that is the companies operating platforms in space, the companies using those platforms to produce something, and the end customers buying those products. Taking these in turn, starting from the back, the end customers on Earth need product prices that make economic sense for them to pay. Then the companies producing the products need to be able to make a positive margin on those products given those prices that end customers are willing to pay. That means their costs need to be low enough relative to the prices, and those costs will include prominently the cost of accessing the space platform they use for production. Lastly, the companies operating the platforms need to be able to achieve an acceptable return on investment, given, among other things, that price that their customers are willing to pay for use of their platform. That means the platform operators' investment in the platform and the operating cost of the platform cannot exceed a certain level. More financially savvy listeners will notice that I'm implicitly mixing concepts here. return on investment, margins, asset turnover, but also know that these concepts are all mathematically related. More in-depth examination of this economic viability across the full in-space manufacturing value chain would take probably a few hours, and the podcast format is probably not ideal for it. In any event, my view is that the value chain is now economically viable for very high-value products, which is why people start with those, like, for example, Z-blend optical fiber, advanced semiconductors, organ tissue, monoclonal antibodies, and so on. We have entrepreneurs working on all of those already. Plus, of course, we have entrepreneurs willing to set up platforms, as we have seen. By the way, it is entirely plausible that the platforms, in particular, will need and will receive government support to help the economic viability at the outset. That will probably come in the form of anchor customer contracts. Fourth ingredient, we need operational viability. And what I mean by that is that we need to be able to do the things we want to do at scale and with ease. Given the number of potentially upcoming platforms, as we have seen, and the existing integration partners, I'm optimistic here. Fifth ingredient, we need entrepreneurs who turn the potential of all of this into reality. And frankly, it's a mixed result so far. We have a fair number of entrepreneurs whose companies are setting up platforms, as we have discussed a few minutes ago. We have much fewer entrepreneurs so far pursuing businesses that use these microgravity platforms to do something, whether the use case examples we already mentioned or other things. And this, to me, makes intuitive sense. Setting up a credible business for such a use case typically requires an interdisciplinary team. You need a team, for example, that understands space, but also biology, or space, but also semiconductors. And such interdisciplinary teams are still few and far between, largely as the specialists in the non-space fields like biology and semiconductors do often not yet understand or have heard of what is happening in the space sector right now. And so we're back to the outreach and education challenge. Sixth ingredient, we need investors willing to place bets in this domain. That is slowly improving. Both platform and application companies have been able to attract VC, venture capital funding, substantially from space VCs and from some general deep tech VCs. The most recent example is European space VC Expansion investing in a company called ExoBiosphere, who want to conduct high-throughput drug testing in orbit. Specialist VCs from relevant non-space sectors have by and large not played in this field yet, though. For example, biotech VCs. It's the outreach and education challenge once again. Seventh ingredient, we need some regulatory clarity. And this includes many things. And again, it could be its own episode, probably for a few hours, and just some examples. What regulatory standards will on-orbit biological production have to follow for their products to be acceptable to regulators on Earth? On Earth, we have things like GLP and GMP. Who is even the relevant regulator? Where and how can downmass companies bring their capsules back to Earth? That's not trivial. Just ask VADA. You can look that up in the news. And a popular current topic, will there be tariffs on stuff coming back from space? How does that even work? Anyway, let's wrap up here. So why did I decide to record this particular episode right now? Why not a briefing episode on Earth observation or space debris or something else? In my humble opinion, I think the time is now right for in-space R&D and manufacturing to take off as all the stars are aligning. Okay, excuse all the puns. Okay, some of the following will be slightly repetitive, but I really want to drive these points home. So how are the stars aligning right now? We actually know a lot of the use cases that make sense and for which the concept has been technologically proven on a small scale, thanks to the thousands of experiments already conducted in microgravity. Scalability now seems on the horizon thanks to all the potential upcoming microgravity platforms. It looks like that scale will also be available at a cost point that makes businesses economically viable. Look, I'm not naive. I know ISS access has been effectively subsidized and that all the upcoming platforms still have to prove they can actually operate at the price points they currently promise. But I'm optimistic. And the benefits of researching and manufacturing in space are ever so slowly creeping out beyond of what we often call the space bubble. For example, nowadays you see more and more panels or talks on this topic at non-space conferences like bio conferences. Still, this outreach and education of non-space sectors remains the biggest to-do for all of us enthusiastic about this domain. And again, that's why I'm doing this episode and a few other things. Now, With this excited view of the future for in-space R&D and manufacturing in mind, my space VC fund, E2MC, Earth to Mars Capital, has recently partnered with the ISS National Lab and fellow investment firms Siri and Stellar Ventures to launch the Orbital Edge accelerator. Startups that can leverage the International Space Station, the future other stations and free flyers, and make it through our selection process can get up to $500,000 of VC funding and possibly a sponsored flight to the ISS. Leveraging the ISS here, by the way, does not only include in-space experimentation and manufacturing, but also other potential businesses. You can read more on the Orbital Edge website at https://orbitaledge.techconnect.org. We will also put that domain into the episode notes. Anyway, I hope you found this short introduction useful. And as I said, there's much more to come. Thanks for listening. And that's it for another nominal episode of the Space Business Podcast. And once more, if you enjoyed this episode, please leave us a 5-star rating on your favorite podcast platform, such as Apple or Spotify. You can follow us on Twitter at podcast_space. We're also on LinkedIn under the Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may even include yourself if you have an exciting space story to tell, or interested in becoming a sponsor, or really for any other suggestions, you can drop us an email at spacebusinesspodcast@gmail.com. Thanks so much for listening, and see you for the next episode.